Hey Math 137 friends, welcome to the only section that we're going to cover in Chapter 10, 10.4. This is an introduction to exponential functions. An exponential function is any function of the form y equals b to the x power, where b is greater than 0, we call that the base, and b is not equal to 1. This is called the base of the exponential function. So now our inputs are going to be the powers of this base, and the output is that base to the given power. Why do we avoid b less than 0? Well, if b is less than 0, we would get we could get imaginary numbers in the evaluation of the function. To avoid imaginary outputs. For example, y equals -4 to the x power. If x equaled 1/2, we would have y equals -4 to the 1/2, which would be 2i. And we want to avoid imaginary outputs. We avoid b equals 0 because we would just have the constant function 0 to the x power, which equals 0. And if we had b equals 1, it would be 1 to the x power, which is just 1. And these are constant functions. And they're just not all that interesting. So we just avoid those. So when we define an exponential function, we talk about y equals some number b to the x power. Base of the exponential function is constant. That's not going to change. And the values of the input are what are changing and producing real number outputs. And just a reminder, the difference between equation notation and function notation. Equation notation, we're going to have, for example, y equals 2 to the x. Function notation simply replaces the y with f of x and would get f of x equals 2 to the x power. So let's look at it in function notation and remind ourselves how we use function notation. So f of x equals 2 to the x. Let's find f of 1, f of 2, f of 3, so forth and so on. Well, f of 1 would just be 2. We keep the base 2 constant, and our new input, our input is the power on the 2. So 2 to the 1, which would just be 2. F of 2 would be 2. My base is constant at 2, and then the input would now be the new exponent. So it would be 2 to the second power, which is 4. F of 3 would be 2 to the third power, which is 2 times 2 times 2, which is 8. Now we can have negative exponents, just a reminder. This would be 2 to the -1 power, which means 1 over the 2 power, or 1/2. F to the -2 would mean 2 to the -2 power, which is 1 over 2 squared. The output would be 1/4. 2 to the -3 power would means 1 over 2 cubed, so forth and so on, which would be 1 over 8. Now be careful, our inputs for exponential functions can be anything, including fractions. So this would be 2 to the 1/2, and just remind yourself 2 to the 1/2 means the square root of 2. The square root of 2 is an irrational number, so we can approximate it to be about 1.4-ish, but it's an infinite non-repeating decimal. Oops, not sure why this guy's down here. I'll have to get rid of him. We already did f of 1 up there. All right, so notice we can put in whole numbers, we can put in fractions, we can put in negative numbers, we could actually put in any number. So the domain of the function f of x equals 2 to the x is all real numbers. We can go from -infinity to infinity. All right, let's use these above points that we established to graph this function. Let's see what this exponential functions look like once we graph it. When we put the input 1 in, we were at 2. When we put 2 in, we were at 4. When we put 3 in, we were way up here at 8. So notice this grows quickly as we move to the right. It's going to shoot up. At 4, we would be 2 to the 4, it'd be 16. It'd be way off our viewing rectangle. It would be way up there. At 0, well, 2 to the 0 is 1. Oh, that's probably what I wanted to put here. I go back here and I do f of 0. Well, that would be 2 to the 0. And remember, any non-zero number to the power 0 is just 1. That's probably what that is. That's just a typo. But at 0, we're at 1. At -1, the output was a half. At -2, the output was a quarter. At -3, the output was -1/8. So notice what's happening as we move to the left. The outputs are getting smaller, but they're never, ever, ever going to actually reach the x-axis. If we did -4, it'd be 1/16, and then it'd be 1/32. So something interesting, a graphical feature called an asymptote is happening over there, and I'll write that down in a minute. At 1/2, it was the square root of 2, which was about 1.4-ish, and we'll see that if we go over to a half, 1.4 is about right here, so that falls right in line. Right, and this is what the graph of our exponential function looks like. As we move to the right, it shoots up to the right. As we move to the left, it keeps going down, but it never crosses the x-axis. It's going to skim against it. So this graphical feature is called an asymptote. So let's write this down. As we move to the left, what we say here is x goes to -infinity. So if I put in -4, -5, -6, the graph gets closer and closer to the x-axis, but never touches it. When this happens, we say the function f of x has a horizontal asymptote at the x-axis. Asymptotes don't have to be at the x-axis, but in this case it is the x-axis. And just a friendly reminder, the x-axis is equivalent to the horizontal line y = 0. The domain is our allowable set of inputs, and we can put anything in for x in the exponential function y = 2 to the x. But notice, no matter what we put in for x, all my outputs fall above the x-axis. So the range, all my y values are greater than 0, and we would write that as an open interval from 0 to infinity. We don't include the left endpoint 0 because there is no input that will produce an output of 0. The domain is all real numbers from -infinity to infinity. So there is the graph, our first exponential function. F of x equals 2 to the x. All right, let's generalize exponential functions. So that was just y = b to the x. I'm just going to make it a little more general. I'm going to say y equals, we're going to throw a constant out front, a times b to the x. All right, so my input variable is the power on b, on the base, and this is constant. The base has to be positive and can't be 1. Those are not interesting cases. This is my input variable is x. That may change dependent on the problem, but it's usually pretty clear. Y is my output variable. Right, and then we call this number out front. That power is only touching the b, so this power doesn't apply to that number out front. This is called the coefficient. The only restriction on the coefficient is it can't be 0, because then if it was 0, we would just have the constant function y = 0, which again is not all that interesting. The domain of all exponential functions is all real numbers, unless otherwise stated. It's an application problem, perhaps, maybe input is time and we can't go back in time. So unless otherwise stated, It's all real numbers. All exponential functions have exactly one horizontal asymptote. And it's always y equals some number. It's a horizontal line. And the range of the exponential function depends on this horizontal asymptote. If you remember back to our quadratic functions, the graph of the parabolas, the range depended on the y coordinate of the vertex. Everything fell above that or below that y value. Likewise, with exponential functions, the range is everything above the asymptote or everything below the asymptote. The range of exponential function depends on the horizontal asymptote. So here's an example of an exponential function. We can see that it's leveling out about right here. With this would be the line y equals, I'm just going to call it some constant c. So the range would be, in this case, because it's everything above c, it would be from c to infinity. Everything, so wherever this crosses, it could be at 1, I'm not quite sure. I'm just in generalizing. All right, so here's some examples of some exponential functions. Y equals 2 to the x is the first one that we saw, right? We would say that the base is 2. The coefficient out front that we don't see is 1, because it's 1 times 2 to the x. This one's a little bit clearer. The base is 6, and the coefficient is 1/2. So if we were to put a value in here for x, like an input, we would only raise 6 to that power and then take this result and multiply it by 1/2. We'll see that in a little bit. Right here, g of x equals -4, 1/3 to the x power. The base is 1/3. That's the only thing that has the power applied to it. The coefficient out front is -4. Coefficients can be negative, bases may not be. All right, be really careful here. Y equals -4 to the x. The base is not -4. What you need to think of is what this really means. Y equals -1 times 4 to the x. The base is always positive. A negative mark like this out front really means -1 times that. So the base is 4 and the coefficient is -1. All right, so let's just generalize that. So if you have -a to the x, this is not equal to -a to the x power. It's not the same thing. So here, the x would only apply to the a. Here, the x would apply to everything. All right, so for example, -2 to the 4th power versus -2 to the 4th power. -2 to the 4th power really means, well, this 4 only applies to that 2, so that really means -1 times 2 to the 4th, which is -1 times 16, which is -16. But if we did -2 to the 4th power, this 4 applies to the 2 and the negative, which would be -2 times -2 times -2 times -2. So that 4 applies to the negative out front of the 2, which would be +16. So be really careful when doing that evaluation. So let's look at the function y equals -2 to the x more in general and make a table of values. If x is 1, it's going to be -2 to the 1 power. So we do 2 to the 1 first, which is 2, and then put the negative out front. It would be -2. If x is 2, -2 squared, well, we would square the 2 first. So for example, when x was equal to 2, this would be f of 2 would be -2 squared, which means -2 times 2 is 4. It'd be -4. And in the same fashion, if we put 3 in, 2 cubed is 8 with a negative out front, would be -8. Be careful here. We put in 0. 2 to the 0 is 1 with a negative out front, would be -1. Now be careful with negatives. Negative exponents don't change the sign of the base. So this would be f of -1, which is -2 to the -1 power, which is -1 over 2, -1/2. because we cover up this. 2 to the negative 1 is the 1/2 with the negative out front. Negative 2, 2 to the negative 2 is 1/4, the negative out front. 2 to the negative 3 would be 1/8 with a negative out front, negative 2 to the negative 3, and 1/2 would be negative square root of 2, which would be about negative 1.4-ish. All right, let's plot a few of these. At 1, notice this time we're below the x-axis, we're at negative 2. At 2, we're at negative 4. At 3, we're way down here at negative 8. At 0, we're at negative 1. Negative 1, we're at negative 1/2. So notice we have the same behavior happening. It's just happening on the flip side. Right, and at negative 1, that would be my 1.4-ish right in there. So we have this behavior on the left where it's approaching the x-axis. This time it's happening from underneath. If we take a look back at this graph, oops, nope, not that one, even back further, there we go. If we take a look at this guy, notice if we take this guy and just flip it over, we're going to get the graph that we just drew. So a negative out front just flips the graph over the asymptote. So we have in this case, we have a horizontal asymptote, I'm abbreviating it HA, still at the line y equals 0 at the x-axis. The domain is still all real numbers. Now the range, this time we have to be careful. The range still depends on the horizontal asymptote. So our range is always the numbers above the horizontal asymptote, or all the outputs are below the asymptote. In this case, they're below, so we always put the negative infinity on the left. So negative infinity, and then they stop at 0. We don't include that value. All right, be careful here. We can find the y-intercept. The y-intercept is where it crosses the y-axis. It's when x equals 0. Right, so we can do this, like we can kind of think of this, right? So the y-intercept is when x is 0, and it's at the point 0, negative 1, right? No x-intercepts. Sometimes they do. Not in this case, though. No x-intercepts. So there's everything we need to know about that graph. All right, let's just do a quick refresher of our horizontal and vertical lines. All vertical lines have equation of the form x equals some number, and the last time we saw these was when we were looking at the axis of symmetry for our quadratic functions. So if I just looked here, there's 0, 2, 4. Let's just suppose I looked at this line right here. This vertical line would have equation x equals 3. Every point on this line has x coordinate 3 regardless of what y is. All horizontal lines have equation y equals some number. So let's suppose we were down here. I'm going to cross right here through negative 2. On the y-axis, this would be y equals negative 2. So no matter where we are on this horizontal line, the y-coordinate is negative 2, regardless of what x is. So our horizontal asymptotes will all have equation y equals a number. When we were talking about quadratic functions, the axis of symmetry all had equations x equals a number. All right, let's graph this function. Let's get a little bit trickier. F of x equals 1/2 x plus 3, labeling all our important features. And so I'm going to start at 0. If I put 0 in, now this is an afterthought, I put in 0. 1/2 to the 0 power is 1. 1 plus 3 is 4. All right, so f of 0 would be 1/2 to the 0 power plus 3. Well, 1/2 to the 0 power is 1. 1 plus 3 is 4. At 1, f of 1 would be 1/2 to the 1 power plus 3, which is 3.5, but we don't really say 3.5, right? We say 3.5, well, we say, I'm going to say 1/2 plus 3. I'm going to turn this into 6/2. This is going to be 7/2, but when we graph it, we can think 3.5. So at 1, we're at 7/2. At 2, we're going to be 1/2 squared plus 3, which is 1/4 plus 3. We'll turn 3 into fourths, which is 12ths, which is 13 over 4. So it's 3 1/4, 13 over 4. If I put 3 in, I'll let you do that. We're going to get 1/8 plus 3. Well, 1/8 plus 3 is 3 1/8, or 25 over 8. right, be careful with -1 here, f of -1. If you remember our cool trick, when we're raising a fraction to a negative power, it's equivalent to its reciprocal to that positive power. Right, so that's going to be 1/2 to the -1 is just 2 over 1 to the 1, which is 2, plus 3, which is 5. So that's going to be 5. I put -2 in. That's going to be 2 squared. 4 plus 3 is 7. And then I put in -3. That's going to flip it and make it 2 cubed, which is 8, which is 11. So let's plot these few points and see what we have going on here. We have at 0, at 4. At 1, we have 7/2, but we see that that's 3.5. So at 1, we're at, there's 3, there's 3.5. At 2, I was at 13/4, which was 3 1/4. So it's about right here. At 3, I was at 3 1/8, or 25/8. So I'm just up here. And if you notice that leveling out happening, that is what's going on as we move to the right this time. At -1, my output was 5. At -2, my output is 7. At -3, my output is way up here at 11. Right, so I still have this general shooting up. This time the shooting up happens to the left. One side is always going to shoot up while the other side is going to level off. And I'm going to assume this is going to level off at 3, and I will tell you why in a minute. Right? So the domain is, as always, all real numbers, so from -infinity to infinity. All right, here, I know that this is going to level off at 3. So I'm going to throw in right here my horizontal asymptote at the horizontal line y = 3, and I know that it's going to level off at 3 because anytime you subtract or add a constant to the end of the exponential function, that's where your horizontal asymptote is going to be. This is never going to be 0, but it's going to get infinitely close to 0, so we're going to keep adding numbers to 3, never going below 3. So my horizontal asymptote is 3, so therefore my range, well, notice every point on this graph or every output is above 3. So it's always depends on the horizontal asymptote. So it goes from 3 and then it shoots up to infinity. So my range is from 3 to infinity. My y-intercept, well, it's when x is 0. So when x was 0, we put 0 in. My output was 4. And then notice again, we have no x-intercepts. So that's everything we need to know. Not too terrible, huh? All right, let's try one more. Graphing. All right, 1/4 to the x power minus 4 this time. So 1/4 to the x power minus 4. Well, at 0, f of 0 will be 1/2 to the 0 power minus 4. Well, 1/2 to the 0 power is 1. 1 minus 4 is -3. Now I'm going to give you a hint. I know my horizontal asymptote is going to be at -4. So that's -3. At 1, f of 1 would be 1/2 to the 1 power minus 4, which is 1/2 minus 4, which is -3.5. So notice it's getting lower, but it's never going to go below -4. F of 2 is going to be 1/2 squared minus 4, which is 1/4 minus 4, which is -3.75. And I'm using decimals because they're exact answers. At 3, we're going to have 1/2 cubed minus 4, which is 1/8 minus 4, which is about -3.875. Sound good? All right, now be careful with our negatives. F of -1 is 1/2 to the -1 minus 4. But remember, 1/2 to the -1 is just 2 because we flip it and change the power. 2 minus 4, which is -2. I'm running out of room. Can I fit them in? F of -2, 1/2 to the -2 minus 4. Well, 1/2 to the -2 is 2 over 1 squared, which is 4 minus 4, which is 0. And then we'll squeeze this guy in, f of -3, 1/2 to the -3 minus 4. Well, 1/2 to the -3, we flip the fraction, so that's 2 cubed, which is 8 minus 4, which is 4. All right, let's plot these guys. So at 0, we're at -3. At 1, I'm at -3.5 right here. At 2, I'm at negative 3.75. At 3, I'm at negative 3.875. So notice as I move to the right, we have that leveling out behavior. At negative 1, I'm at negative 2. At negative 2, I was at 0. And at negative 3, I was way up here at 4. So I can see the shooting off as we go to the left. So as we go to the left, it's going to shoot off, up, and as we go to the right, it's going to level off. So always, all exponential functions shoot off in one direction, they level off in the other. If it was a different function, it would look like this. It could level off to the left, shoot off to the right, could be upside down, or it could shoot off to the bottom left, but level off as we move to the right, so forth and so on. So all our important features, well, our domain is all real numbers. Right, we have a horizontal asymptote right here at negative 4. So it's at the line y equals negative 4. So the range is everything above negative 4. Right, we have a y-intercept right here at negative 3. Y-intercept was when x is 0. Now notice this time we do have an x-intercept. My x-intercept is when y is 0, and that happened when x was negative 2. I think we got it all. So this one had the extra feature, the x-intercept, that the others did not. So let's just generalize. All exponential functions take on one of the 4 shapes. So exponential function in general, a times b to the x power. If a is positive and b is greater than 1, it's going to shoot off to the right and level off as we go to the left. Now you don't have to remember exactly all 4 of these patterns, but if you just remember the general shape and you plot a few points, keeping in mind that it shoots off in one direction and levels off in the other. If a is positive, but your base is a number between 0 and 1, it's going to shoot off to the left and level off as we go to the right. So these are my horizontal asymptotes. If a is negative, your coefficient out front is negative, but b is greater than 1, then it's going to be underneath the asymptote, and it's going to shoot down to the right and level off as we go to the left. If a is negative, it's going to still fall under the asymptote, but if b is a number between 0 and 1, it's going to level off as we go to the right and shoot down as we go to the left. So you just have to remember it's going to take on one of these 4 general shapes. You plot just a few points, identify the asymptote. The asymptote is always going to be what's tagged on right here. This will be your horizontal asymptote, whatever you add or subtract. And if you're adding or subtracting nothing, the horizontal asymptote will be at the line y equals 0. All right, one little last tidbit of thing in this section, and we're going to solve some exponential equations. So again, just a reminder, between an expression and an equation, an exponential expression would just be something of the form like 2 to the x. And we would evaluate this, simplify if it was possible. An exponential equation, we would take our expression and we would assign it a value. And we solve these guys. So this we either evaluate or simplify. This we would solve. So that's what we're going to do. We're going to take a minute and solve a few exponential equations. In order to solve exponential equations, we're going to use what we call the one-to-one property for exponents. It's a helpful tool and help us solving exponential equations. It's very simple. If we have a base to a power and we have the same base to a power, then simply the powers must be the same. All right, so how is that helpful? Let's look back at this guy solving this exponential equation. If I'm solving 2 to the x equals 16, isn't 16 just 2 to the 4th power? 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is equivalent to solving 2 to the x equals 2 to the 4th power. So if I can get the bases to match, then using this one-to-one property of exponents, I can just set the exponents equal. So x must equal 4, and we just solved it. So we put 4 up there, 2 to the 4th equals 16. And you might pick, well, that was a little bit of overkill. I could have just looked at that and said that, but we're going to get a little bit trickier, of course. let's suppose I had this instead. I had 2 to the power 3x minus 7 equals 16. Well, our goal here is to get the bases the same, and we can write 16 as base 2. So we're going to keep this as 2 to the 3x minus 7 power and rewrite 16 as 2 to the 4th. Now that we have equal bases, the one-to-one property says we can just set the exponents equal. 3 to the x minus 7 equals 4, and then we solve for x. 3 to the x equals 11, x equals 11 halves. So now 11 thirds, whoops, I was writing it, just wasn't saying it. So it's not so obvious when we look at here that x would be 11 thirds, but when I rewrite 16 as 2 to the 4th power and set my exponents equal, we change this exponential equation into this cute little linear equation for then we just solved and we got 11 thirds. And you can check, plug it in, and you'll see that it works. Right, here's where it gets a little bit trickier. What if I said 2 to the 4x plus 6 equals 1 over 16? Well, I want to write this as 2, leave the 4x plus 6, and can I write 1 over 16 as 2 to some power? Well, keep in mind, 16 is still 2 to the 4th power, but because it's in the denominator, 1 over 16 is equal to 2 to the negative 4 power. So if what we're looking for is in the denominator, we can just change the exponent to negative, and then it will give us the expression that we have. So 1 over 16 can be written as 2 to the negative 4 power. So 2 to the power x to the 4x, 2 to the power 4x plus 6 equals 1/16 is the same thing as solving 2 to the power 4x plus 6 equals 2 to the negative 4. Now that we have the same exact base, I can just set my exponents equal. The one-to-one property for exponent says that 4x plus 6 must equal negative 4. And then we solve for x. Subtract 6, we get 4x equals negative 10. Divide by 4, we get x equals negative 10 fourths. We simplify, that's negative 5 halves. And you can go and you can plug that in, plug in negative 5 halves. You're going to get 2 to the 4 times negative 5 halves plus 6. 4 times negative 5 halves is negative 20 halves, which is negative 10. Negative 10 plus 6 is negative 4. 2 to the negative 4 is 1/16. All right, and this is the last one, and this is the trickiest. Of course, I saved the best for last. All right, 27 to the 2x equals 9 to the 1x minus 3. What we want to do is get a common base. 27 is not 9 to a power, and 9 is not 27 to a power, or not a nice power. But if you can think of a base that these guys have in common, so we're going to make a little side note here. And if you're good at your powers, you'll notice that 27 is just 3 cubed, and 9 is 3 squared. So we can turn these both into base 3. So 27 to the 2x equals 9 to the 1 minus 3x. So I'm going to write 27 as 3 cubed, but now we have to be really careful because that's 3 cubed to the 2x power. And I'm going to rewrite 9 as 3 squared. And that's all to the 1 minus 3x power. So my common base, the base that 27 and 9 have in common, is 3. So I rewrote 27 as 3 cubed and 9 as 3 squared. But then I have to raise 3 cubed to the 2x power and 3 squared to the 1 minus 3x power. So here's where your properties of exponents come in handy. Powers to powers. Remember to simplify powers to powers, we multiply. So 3 cubed to the 2x power is equivalent to 3 to the 3 times 2x, which is 6x. Be really careful here because we have to distribute that 2. We have to multiply it by that entire power. So this is going to be 3 to the power 2 minus 6x. Now that we have it all straightened out, we have no parentheses. We have 3 to some power equals 3 to what looks like a different power by the one-to-one property. We can now set the exponents equal. 6x must equal 2 minus 6x, and we solve for x. I will add 6x to both sides, and I get 12x equals 2. Divide by 12, and I get x equals 2/12 or 1/6. All right. So that is my final answer. All right, kids, have fun with that. Last section. Good job. Talk to you soon.